Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 1, Lesson 4 on equivalent expressions. Today's lesson, strangely enough, is one of the most important basic lessons in all of algebra. So let's right away get into what equivalent expressions are. All right, so equivalent expressions. These are two or more algebraic expressions are equivalent if they have the same value for every value of the substitution variable or variables. In other words, no matter what you stick in for the variable, the two expressions come out to be equal when they're evaluated. And this is very, very important because often when we're solving equations or manipulating expressions or something like that, what we're really doing is we're just replacing one expression with one that's equivalent to it. So let's take a look at exercise number 1 and see if we can spot two expressions that are algebraically equivalent. Exercise number 1. Consider the three expressions below. By substituting in the values of x given, determine which two expressions are equivalent. Show your calculations and circle your final answers. All right. So in other words, we've got these three expressions. 5 times x minus 3, 5 times x minus 3, and then 5 times x minus 15. Now, really, to establish that two expressions were equivalent, we'd actually have to test every single real value of x, which is impossible. That would take us until the end of time, and we can't do that. So what we're going to do is we're just going to take these three values of x, we're going to substitute them into each one of these expressions, right? And we're going to generate some evidence, at least, about which two expressions are equivalent. So let's do the first line together, and then we'll have you do the second two values of x on your own. All right, let's go to the board. So for x equals 7, what we want to do is we just want to put it into this expression, 5 times 7 minus 3. Of course, order of operations tells us that we've got to do the 7 minus 3 first, which is equal to 4. And then we're going to do that product, 5 times 4, and we're going to get 20. All right, so the first expression has a value of 20 when x is 7. Now the second expression, right, that'll be 5 times 7 minus 3. Now we know from order of operations we've got to do that product first. That's going to be 35 minus 3, and of course 35 minus 3 is 32. That final expression, right, we're going to put x equals 7, or x is 7 in, right? We'll have 5 times 7 minus 15. Again, 5 times 7 is 35, and then we're going to subtract the 15. Let's get a little subtraction there, otherwise it's going to look like multiplication, and that's equal to 20. All right. Now, we already have some evidence, obviously, that this expression and this expression are equivalent, because when we put x equals 7 into both of them, we got a value of 20 and we got a value of 20. And one thing that we know for certain is that this expression and this expression are not equivalent, right? Because if they were equivalent, they would have had the same values for that x value of 7. What I'd like you to do now is pause the video, take some time, evaluate everything for x equals 0 and everything for x equals -2, and then let's come back and talk about our results. All right, so I'm going to go through all 6 evaluations together. All right, and I'm going to walk through them a little bit faster than I did here because the order of operations issues are still the same. So I'm just going to be going kind of through the arithmetic, and let's see what we find. First for x equals 0. All right, here we go. Right, I'm going to put x equals 0 into here. I've got 5 times 0 minus 3. 0 minus 3 is -3. 5 times -3 is -15. A positive times a negative is a negative. All right, in this case, we're going to have 5 times 0 minus 3. Here we do that product first. 5 times 0 is 0. And 0 minus 3 is -3. And in the last expression, we're going to have 5 times 0 minus 15. Again, 5 times 0 is 0. Minus 15 gives us -15. All right, let's go for that x equals -2. We're going to have 5 times -2 minus 3. -2 minus 3 is -5. 5 times -5 is -25. Here, let's put in that -2 again for x. 5 times negative 2 minus 3. 5 times negative 2 is negative 10 minus 3, and negative 10 minus 3 is negative 13. Finally, we've got 5 times negative 2 minus 15. 5 times negative 2 is negative 10. Negative 10 minus 15 is negative 25. All right, so we have now developed a lot of great evidence that suggests that the first expression and the last expression are equivalent, right? 20 and 20, negative 15, negative 15, negative 25, and negative 25, right? So what we can tell from this is, at least for those three values of x, those two expressions have the same value. So in all likelihood, this expression and this expression are equivalent. And now let's talk about how we know that they're equivalent in exercise number 2. Let's take a look. Which property, the commutative, associative, or distributive, justifies the equivalency of the two expressions you determined to be equivalent above? All right, so let's compare them, right? One of those expressions was 5 times x minus 3, and the other expression was 5x minus 15. Pause the video now and ask yourself which of those three properties of real numbers, the commutative, associative, or distributive, justifies that these two expressions are in fact the same expression that just look differently. Well, it's the distributive property. Remember, the distributive property says, look, if I've got, something multiplying, let's say, a sum or a difference, right? Then I can multiply that sum or difference through, right? And then have the addition. So in this case, that 5x minus 3, right? The distributive property, right? If I multiply through, says 5 times x minus 5 times 3, and that is our other expression. So it is the distributive property that's going to justify that those two are the same. And again, this is amazingly important. When we manipulate equations, when we manipulate expressions, almost always what we are doing is using one or more of those three properties, commutative, associative, or distributive, to simply play around with the expression, change it so that it looks different, but it has exactly the same values as the original expression for the same value of x. Really, really critical. Let's keep working with equivalent expressions. All right. Now, we will often use the distributive property along with the others to write more complex expressions in simpler forms. And let's see a good example of that in exercise number 3. Let me just bring it to the top of the board. And now let's take a look at it. Which of the following expressions is equivalent to 5 times 2x plus 1 minus the quantity x minus 3? Show your work to justify your response. Evaluate both expressions for x equals 4 to check to make sure you have the correct answer. All right, so let's talk about this a little bit, right? This is a fairly complicated expression, right? And you could imagine maybe that expression calculates, I don't know, the profit you make from selling X donuts or something weird like that, right? It would be nice to have that expression in a much simpler form because it's just easier to work with, easier to calculate with. Now, these are definitely the types of problems that you did do a little bit of work on in middle school. So what I'd like you to do is pause the video now, play around with the distributive property, combining like terms, a variety of different things in this expression to see if you can figure out which one of these it's algebraically equivalent to. Pause the video now and take a few minutes. All right, well, let me write down the expression first and let's take a look at it. We've got 5 times 2x plus 1 minus x minus 3. All right, so I'm going to use the distributive property first on this 5. So I'm going to have 5 times 2x, which is 5 times 2, or 10x, and then 5 times 1 is 5. Now this is maybe a little bit trickier, and it might be easiest to view this as adding a negative 1 times x minus 3, all right? So when I do that, I can then distribute a multiplication by -1, so -1 times x is -x. Maybe put parentheses around that. And -1 times -3 is +3. I can now use some associative, commutative properties of addition to get 10x plus -x plus 5 plus 3, right? And now 10x plus -x is 9x, and 5 plus 3 is 8. Okay, so the equivalent expression is 9x plus 8. Now, a lot of people will make a mistake on this problem, and they might at this point have 10x plus 5 minus x minus 3. Now, if you think about that, that would have left us with 5 minus 3, and it would have left us as a final answer with 9x plus 2, right? Which is this choice down here. So it's very easy to get fooled on here because, you know, you're subtracting a negative, which turns it into a positive, and, you know, two wrongs don't make a right, all that, but two negatives make a positive. It could easily be that you make a mistake on that. So what's really cool is we can test the equivalency by grabbing a random value of x. Okay, in this case, I suggested x equals 4, but you could really take just about any value of x you want, substitute it into this monster expression, check its value, substitute it into this much more easy expression, check its value, and if they're the same value, you have some confidence that the two expressions are equivalent. If they're different values, however, it either means that the two expressions are not equivalent, or you just simply did the evaluation wrong. So let's do the evaluation really quickly for x equals 4. Let's go to the board. All right, so I'm going to do it in the original first. That's going to be the much more difficult one, and that's kind of the point, right? So I have 5 times 2 times 4, I'm going to use the dot here for multiplication, plus 1, minus 4 minus 3, right? That's going to be 5 times 8 plus 1 minus 1. I don't really need it in parentheses anymore. I have 5 times 9 minus 1. That's going to be 45 minus 1, and that's 44. Now, just before I substitute it into the simpler expression, I want you to consider the fact how many different lines I needed and how many different calculations I needed in order to evaluate the original expression when x was 4. Now let's see how easy it is to evaluate it in the simpler expression, this one. So now let's go in the equivalent. Right? In the equivalent expression, maybe do a little line here so we don't get all messed up. We have 9 times 4 plus 8. 9 times 4 is 36. And 36 plus 8 is 44. All by itself, that wouldn't prove that the two expressions were equivalent, right? Because two obviously non-equivalent expressions can have the same value for the same value of x. That can happen, obviously. But had we made that mistake with the subtraction of 3, and had we checked 9x plus 2 versus this very complicated expression, they wouldn't have had the same answers, right? In fact, this one would have been 6 units smaller, and we would have said, oh, wait a second, I made a mistake somewhere. So let's do a little bit more work with equivalent expressions. All right, exercise number 4. Don't forget that distribution also works with division. So we can distribute division by a particular number just like we can distribute multiplication by a particular number. And we'll see that come up in exercise number 4, which is very similar to the last exercise, but with some division involved. All right, let's take a look. Which of the following expressions is equivalent to 4 times the quantity 3n plus 1 minus 2, all divided by 2, minus 5? Show your work, think carefully about order of operations and properties we've learned. Finally, check your answer by evaluating both the original expression and your answer when n is equal to 1. Show your check. All right, so just like before, I'd like to turn you loose on this one. Take a few minutes, manipulate this expression, and see which one of these 4 choices is equivalent to it. Pause the video now. All right, let's do it. Okay, so I'm going to write down my original expression, 4 times 3n plus 1 minus 2, all divided by 2 minus 5. All right, that numerator, I think first thing I'm going to do is distribute multiplication by 4. That's going to be 12n plus 4 minus 2, all divided by 2 minus 5. I think I'll simplify that numerator. That's 12n plus 2 divided by 2 minus 5. I can now do my distribution of division. That's going to be 12 divided by 2 times n, plus 2 divided by 2, all minus 5. A little more, I've got 6n plus 1 minus 5. And I can really look at that as 6n plus 1 plus negative 5. So ultimately, that's going to be 6n minus 4. Choice 4. Right, there we go. So we do a little bit of distribution, of multiplication. We combine some constants here. We then distribute the division, collect some like terms or some like constants down here, and we get a final answer of 6n minus 4. Again, there's lots of places here where this could go wrong. So now what we want to do, grab that random value of n. In this case, I've suggested n equals 1, substitute it into this expression, substitute it into that expression, and see if they're both equal. Pause the video now, do that substitution, and get a little practice evaluating two expressions. All right, let's do it. So first thing I'm going to do, just like before, is I'm going to go with my original expression first. All right, my original one, the beastly one, is going to be 4 times 3 times 1 plus 1 minus 2, all divided by 2 minus 5. All right, that's going to be 4 times 4 minus 2 divided by 2 minus 5. I'm going to run out of space here. There we go. 16 minus 2 divided by 2 minus 5. 16 minus 2 is going to be 14 divided by 2 minus 5. Wow. And that's going to be 7 minus 5, which is equal to 2. All right. Now the simplified version. My simplified version, look at how quick this is going to be. I'm going to have 6 times 1 minus 4. That's going to be 6 minus 4. And that's also going to be 2. Right? Again, evidence that we've done our manipulation correctly. Right? If we've done the manipulation incorrectly and we grab some test value and we put it in, then in all likelihood the two values will not be the same. All right, let's keep going. Now, one thing that's critical is that the distributive property works in both directions, and that's because equality works in both directions. All right? So, you know, oftentimes people, when they look at something like the distributive property, a times b plus c, and oh, it's a times b plus a times c, they say, well, that's the deal. It's telling us that whenever there's a number outside of parentheses or a variable or something, I should multiply it through. And it really doesn't say that. What it says is that these two things are equivalent, right? That's what equals means. The thing on the left and the thing on the right are the same, all right? Now, that means that we could just literally flip this thing around and say, well, if we've got something that looks like this, a times b plus a times c, I can rewrite it as a times b plus c. All right, we're just literally sort of reversing the distributive property, if you will. Okay? And that is very handy when we have a problem that looks like exercise number 5. Let's take a look. Which of the following expressions is equivalent to 10x plus 15? Explain how you made your choice in the space provided. All right, well, I'd like you to pause the video here and I'd like you to look at the original expression, look at the 4 choices, and think to yourself, which one of those would be equivalent, and keep your eye on the distributive property, because that's what it's going to be all about. Pause the video now. All right, well, one great way of doing this is to literally use the distributive property on all 4 of the choices, and just see which one of them comes out to be this. So for example, just for choice 1. On choice 1, if I use the distributive property, right, and I multiplied through by that 2, I'd get 16x plus 26. Well, I might be crazy, but I don't think 16x plus 26 is equivalent to 10x plus 15. They're just not the same thing. Right? So I could go through each one of these things, multiply through each one of these constants, and what I'd ultimately find is that it's choice 2, right? I mean, in choice 2, if I multiply through by the 5, I'd get 10x plus 15, right? So it'd be choice 2. But here's another way to look at it, right? And you did some factoring back in middle school, right? I've got 10x plus 15. right? And one thing I can say for certain is that 10 is the same as 5 times 2, and then you've got our x, and then 15 is the same as 5 times 3. Now notice, right, there's a 5 that's multiplying both a 2x and a 3, which means we can rewrite this by sort of going in the opposite direction that we normally think of the distributive property, and take that 5 and, quote, factor it out of the expression. Now all we're really doing is rewriting this expression, 10x plus 15, which is really a sum, right? It's a sum of 10x and 15, and rewriting it as a product, specifically as the product of the number 5 with the expression 2x plus 3. Now I'm not saying that this expression is simpler than this one, but I do claim that they're equivalent, and there will be times when this expression, something that looks like this in factored form, is more valuable than something like this in unfactored form. And we'll get into more of that later, but let's get a little bit of a practice in going in the opposite direction with the distributive property. Oh, I gotta get this up here. Let's take a look. Factoring expressions. Factoring is simply the process of writing an equivalent expression that is in product form. That's all it is, writing an equivalent expression, but as a product, as a multiplication, right? So it's like saying, well, I can write 12 as 4 times 3. That's factoring, right? Easy. So let's take a look at exercise number 6. Write each binomial below as an equivalent product of the binomials GCF, that's greatest common factor, and another binomial. All right, so let's do a few of these together, right? When I look at 6x plus 21, I'm thinking about the number 6 and the number 21. And the greatest common factor of the number 6 and the number 21, right? Another way of thinking about greatest common factor is greatest common divisor, is the number 3, all right? So in this case, the GCF is equal to 3. And I can really think about this thing as 3 times 2x plus 3 times 7, right? 21 is 3 times 7, 6 is 3 times 2, right? There's that greatest common factor. So I can write this as 3 times 2x plus 7, right? Simple enough. 3 times 2x plus 7. I can do that in each one of these problems. For instance, if I look at 2y minus 10, and I'm just concentrating right now on the numbers. Later on, in different lessons, we'll also be thinking about greatest common factors in terms of variables as well, but not right now. For right now, we look at 2y minus 10 and we think, well, 2 and 10, what is the greatest number that divides into both of those, that is a factor of both of those? And that's the number 2, right? Simple enough. The GCF is equal to 2. I can think about this as 2 times y minus 2 times 5. Right? There's that 2, in which case this is 2 times y minus 5. I'm just going backwards on the distributive property. Right? I'm writing like if you ever had written out the distributive property line by line, I'm now going, instead of going this direction, I'm going this direction. Okay? What I'd like you to do now is pause the video and take a shot at the rest of these things. See where you can get to, and then we'll go through each one. All right, ironically, letter C might be one of the more challenging ones. We've got 14w plus 14, right? So what we're really doing is we're thinking about the number 14 and the number 14. And if we think about the greatest number that divides into both 14 and 14, it's 14, which is sounding really repetitive after a while, right? So in this case, our GCF is equal to 14, right? And really, that means that we've got 14 times w plus 14 times 1, right? In which case, there's that GCF, and we can rewrite this as 14 times w plus 1. Students will sometimes make a mistake with this, and they'll simply rewrite this as 14 times w. But if 14 times w was equivalent to 14 times w plus 14, that would be strange, right? 14 times w plus 14 is obviously 14 more than just this thing. All right, let's take a look at letter D. Let's bring this second line. Let's hopefully bring this second line up to the top. Now we're going to extend the page a little bit and get it into view. There we go. All right, so next problem, right? We've got 15n plus 10. In this case, the GCF is equal to 5, right? We've got 5 times 3 times n plus 5 times 2, right? We can then factor that 5 out, and we get 5 times 3n plus 2. Let's move right on to letter E. If we look at the numbers 44 and 77, those should look pretty obvious. The GCF is going to be 11, right? So we have 11 times 4x minus 11 times 7. There's our GCF. So we can write this as 11 times 4x minus 7. Maybe circle these so you know what the final answers are. And finally, if I look at 18 and 6, the greatest common factor or divisor of those two numbers is 6, right? We've got 6 times 3c plus 6 times 1, right? That means we're going to have 6 times 3c plus 1. All right. It is very important to be able to go both directions with all the properties, but very much go both directions with the distributive property. All right. Let's summarize. Equivalent expressions, there's my title. Equivalent expressions are some of the most important idea, or is one of the most important ideas in all of math. All right, so much of what we do in terms of algebraic manipulation is basically replacing one expression with another expression that's equivalent to it. And we have permission to do that because if two things always have the same value, right, for the same value of a variable, then one of them can just be put in place of the other. That's really kind of the idea with equivalent expressions. So when you're solving an equation and you simplify the left side or the right side by using the commutative or associative or distributive properties, what you're always doing is you're always just creating equivalent expressions. That's all. That's all. So obviously this is a very, very important skill, very important idea. You're going to get lots of work on it in the homework, and we're going to be seeing it probably every day from now on in algebra. Okay, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.